So let's play a puzzle together. So on that slide here, what you're seeing here is I'm giving you 3 by 3 squares, which are colored slightly differently, right? So I color some of the subset of the 9 subsquares for each of them. So each of the feature vector here is one of the x1 through x6. And I'm assigning a label using a function that you don't know. I know the function, you don't. It's the function f. And I'm claiming that if you look at the top 3 feature vectors, I'm assigning them the label 1, plus 1. And if you look at the 3 feature vectors on the bottom row, I'm assigning them the label -1. And so the trick question for you now is, based on that little data set that I'm giving you, can you tell me what is the label of the unseen, so far, feature vector x7? So it has a different coloring pattern. What is your guess as to what the label is? The answer is that there's no way you can find. And the reason you cannot find is that, number one, I generated f completely randomly, so there's absolutely no structure there. And as a result, it seems like, learning seems quite impossible with that additional assumption, because, depending on the seed I'm using in my random number generator, I'm going to get a different f every time. So what's missing? So what's missing is a very fine point of terminology, which is a distinction between possible and probable. So before we apply that to learning, let's talk about it in a slightly different context. Let's imagine that I flip a coin, and that coin is biased. It lands on head with an unknown probability p. So you don't know what p is. P, could be 1/2, could be 1/3, doesn't matter. You don't know what p is. Now, formally, the model is the following. The probability that it falls on head is p. Probability that it falls on tail is 1 minus p. Now say that we repeat that experiment, and I flip the coin n times. So what I'm mimicking here, p, if you wish, plays the role of the unknown function in machine learning that we're trying to learn. And this n repetition of the experiments, that plays the role of my data set. Okay, I'm giving you n examples of what p could be. So can we estimate p? If you remember a little bit of probability and statistics, you might have seen that one very natural way to estimate p is to say, well, I'm going to count the number of times in my n experiments I got head, and I'm going to divide by n. Okay, so you can make that argument slightly more formal, because using the law of large numbers, that p hat converges in probability to p as n gets large. Okay, so it's a complicated way of saying is that the more samples you get, eventually, the probability that the value of p hat differs by p by more than epsilon goes to 0 as n goes to infinity. That's what it's telling you. Now, one thing that's subtle, but that's quite very important to notice here, is that result is not telling you that p hat is equal to p. It's not telling you that p hat will always be close to p. It's just telling you that it's unlikely that p hat will be very different from p. And that's a very subtle distinction, but it tells us that from a mathematical perspective, there's a huge difference between saying that something is possible and impossible versus saying that something is probable versus improbable. Okay, so for instance, if I were to flip an unbiased coin, p is equal to 1/2 a million times, p hat is probably going to be something like 0.500002. So it's not exactly 0.5, but it's very close to 0.5. Okay? But if I were very unlucky, I could be in a situation when I flipped a million times, I always got tail, from which I would infer that p is equal to 1. Or sorry, p equal to 0. So these results are not saying that it's impossible for me to be very unlucky. It says that it's very improbable for me to get unlucky. And this subtle distinction is something that we have to account when we talk about machine learning, because otherwise, when you look at the function f I was trying to have you guess, there's no way you can guess, because everything is possible. Every function f is possible. But maybe some are more probable than others. But to talk about probabilities, you need to introduce a probabilistic model. And that is something that was missing in our initial attempt to talk about supervised learning. Okay? So we're going to revise our model. And the modification is going to be the following. We're still going to say that our goal here is to find an unknown function. And that unknown function is still out there. We don't know what it is. We're still going to say that we have a data set that contains endpoints. But the big difference now is we're going to say something about how these examples are generated. And the key assumption that we're going to make is that the examples or the feature vectors or the data points, I'm going to use all these terms as synonyms, these feature vectors are actually the realizations of random variables that are drawn IID, meaning independent, identically distributed, according to an unknown distribution Px. Okay, so I'm introducing a probability distribution on the feature vectors. Okay, now the reason I'm doing that is because once I have a probability distribution, I have a probabilistic model, and I can talk about an event being probable, as opposed to just talking about possible, impossible, which doesn't lead us very far. Okay, so that's our first modification of our original attempt to build a supervised learning model. We need to say something about how the examples are generated. And let me take a second here to make two comments. Comment number one, I'm going to start talking about probabilities quite a bit today. Now, I understand that some of you might need a refresher. The self-assessment is here for that, and I will post resources, meaning slides, maybe a video if I find the time, and lecture notes that will go through the minimum you need to remember to take this class comfortably. But for today, if you have doubts as to concepts, what I mean, please stop me and I will definitely reiterate. But I will provide additional material for you to self-study or self-refresh your memory regarding probabilities and statistics. I did it in class last semester. I think it takes a little bit too much of useful class time, so I will leave it to you guys to check that on your own. But if there's ever a doubt regarding notation, terminology, concepts, please ask me. If not live, then on Piazza, and I'll be happy to elucidate everything. Okay, so that's a slightly different model. Okay, so the question then is, okay, is it everything we need to talk about supervised learning? So yeah, maybe not actually. And to highlight what could be missing again, let me give you another puzzle. So you might remember that from a few years back, it became an internet sensation overnight. What is the color of that dress? So just for fun, let's try to see what you think. Gold and white, black and blue. Okay, there's no consensus here. So who's right and who's not right? A bit hard to tell, right? What is the real color of that dress? If you had to run a machine learning algorithm, for computer vision to tell us the color, that's a bit problematic. It's problematic because we, as humans, don't seem to agree on the color of the dress. So if we have to run a supervised learning algorithm and that's a sample, what do we provide as a label? We don't even agree. And so what this suggests here is that in many machine learning problems, when we talk about the function f that we're trying to learn, it's not as simple as that, because the labels that we're trying to put and learn are not necessarily things that are clean. They might be noisy, we might not agree on what the labels are, there might be errors, or there might be no ground truth. It might be impossible to actually assign a color to that dress. And so as a result, we need to modify the model further. And in addition to introducing a probability distribution Px that tells us how the data, how the feature vectors are generated, we need to introduce another unknown conditional distribution Py given x to learn that we have to learn if we want to predict a label. Okay, so again, I think there is a tiny typo. There should be a boldface x because it's a feature vector. Okay, so the idea here is that we need to include in our general abstract model for supervised learning the possibility that the labels are not clean and noisy. And we model that as Py given x. And if you want to think about it, it's a very general model, but one thing that it captures very well is the following, just as an example here. What it means is that it could be that the label that you get to provide as part of the data set are something like yi is going to be maybe the true function f of xi if it exists, but then there is a noise ni that is corrupting. Okay, so that P of y given x is effectively capturing something of that nature. Okay, it could be more general, but f of xi plus ni is a way to describe Py given x. Okay, so one thing that I really want to emphasize is that even though I'm including this Px and this Py given x in my model, they are still unknown quantities, right? I'm not changing the fact that I have to learn something that I don't know, but I'm just saying that I'm assuming that these probability distributions exist, okay? And assuming that they exist is an assumption. I just saw a few days ago, there is a call for proposals from the Army in which they want to revisit that. They're saying, oh, we don't like this assumption that all the data is IID. We want to understand how we can learn when the data is not IID, okay? Spoiler alert, if it's not IID, you can't really do much, but maybe if it's close to IID, you can do things, okay? So that's what they're after. They're trying to challenge, this underlying assumption that we're making to make sure that we're not missing anything, because real world data might not be IID. If you're sampling, for instance, people who like gardening in my neighborhood, you're going to be overly biased towards people who like to have gardens, because we have gardens around here, okay? So we are putting assumptions, but the assumptions are not fundamentally affecting the fact that there's something to learn that we don't know. So the other thing I want to emphasize is that the roles of Py given x and Px are quite different. Even though they're both probability distributions, Py given x really captures what we want to learn. Okay, so the idea is to capture the underlying function that allows us to attribute a label to a feature vector x. That's what we call Py given x. That's really what we care about learning. Because if you know Py given x, you can, given a new x, generate a new label. Px here is something else. It really models the sampling that is used to create the data sets. But in principle, we don't need to learn Px to come up with a model, right? We just need to be able to explain and give a model y, a label y given x, but we don't need to learn Px. And keep that in the back of your mind. It's something that we'll revisit a bit later on when we'll talk about algorithms, because some algorithms try to learn both Px and Py given x. And in a way, they're trying to do too much. And usually there's a price for doing too much in machine learning.